Okay, this is chapter 6.1, perpendicular and angle bisectors. The essential question for this section is, what conjectures can you make about a point on the perpendicular bisector of a segment and a point on the bisector of an angle? So what you will learn in this chapter section is how to use perpendicular bisectors to find measures, use angle bisectors to find measures and distance relationships, and write equations for perpendicular bisectors. Okay, so before we get into any examples, we'll take a look at these two theorems. So they state that in a plane, if a point lies on the perpendicular bisector of a segment, then it's equidistant from its endpoints. So let's take a look here. What we have is a line perpendicular to a segment. So that 90-degree angle confirms that this line is perpendicular to segment AB. These congruent markers state that PA is congruent to PB, and therefore that AB has been bisected into two congruent pieces. If a point is on the line that bisected that segment, then that point is equidistant from the two endpoints of that segment. In other words, CA, the length of CA equals the length of CB, and therefore CA is congruent to CB. Theorem 6.2 is the converse of that. The converse is the reverse of the other. Converse just means that if the conclusion is stated, then we can confirm the hypothesis. So in a plane, if a point is equidistant from the endpoints, so here D is equidistant from A and B because AD is congruent to BD, that means the lengths are congruent or equal, same distance, then this line C that goes through the bisecting point of AB will continue through that point. So if DA equals DB, then point D lies on the perpendicular bisector. So if this line continued, we know it's going to go through D. The proof of that's on example 32 on page 308. And I'm not going to go over that in this video. If you want to take a look at it, have at it. Okay, so example 1 is using the perpendicular bisector theorem. Find each measure. So part A says to find segment RS. So let me just highlight that for starters. That is our goal. We want to find RS, which is right there. Okay, so in order to do that, we have to use a perpendicular bisector theorem. So as you can see, SQ is perpendicular to, and that's line SQ, so I'll be very careful. Line SQ is perpendicular to segment PR because of this 90-degree angle. Line SQ is a perpendicular bisector of segment PR because this is that. Okay, we know that this split PR in half, so that's a perpendicular bisector. So since that's a perfect perpendicular bisector, point S is on SQ, line SQ. Therefore, SR is equal to SP. Okay, a point on the perpendicular bisector is equidistant from the two endpoints. So now I can say SR equals SP. And since SR equals SP and SP equals 6.8, SR must also equal 6.8. Okay, so that's how you do this. B, segment EG. We want to know what the length of, let me highlight it. And I didn't use a thick enough highlighter last time. Let me go a little thicker. We want to know how long EG is. Okay, so in order, what were we given? EH is congruent to GH. Okay, so that is a side congruent to a side. We have a point H that is equidistant from both endpoints of EG. And we have FH is a perpendicular to. So I can't say it's a bisector yet, but I can say line FH line FH is perpendicular to segment EG. Okay. Point H is on FH, obviously. Okay, so it is a point on a perpendicular line to a segment. And since EH equals HG, but actually GH, EH equals GH, then FH must be a perpendicular bisector. Okay, so that's line FH. So let's recap. Line FH is perpendicular to EG, given by that 90-degree angle marker. Point H is on that line, and HE and HG, or EH and GH, are equal. So that means that this point is on a line that intersects at a 90-degree angle, a segment, and that point that's on that line is the same distance from the endpoints. Therefore, that concludes, we can state that FH is a perpendicular bisector of segment EG. And since that's true, then EF is equal to FG, and therefore EF, the length of EF, is also 9.5. All righty, so that's how you do these. So now we have AD. So let me get my highlighter, and now we want to find, oh, thought I changed that to thin, Control Z, AD. Okay, so I want to find AD, which is right here. Okay, so what do we know? Well, BD is perpendicular to CA. So I'm going to say line BD is perpendicular to segment CA. Okay. And notice CB is congruent to CA. So since CB equals AB, or I should say is congruent, segment CB is congruent to segment AB. Since they're congruent, then line BD is a perpendicular bisector of segment AC. And now we have a point D right here. And now we can say point D is on BD. And since point D is on BD, then the distance to the endpoints are equal. So now I can say AD has to equal CD. And since AD equals CD, then we can substitute in our givens. AD is 5x and CD is 3x plus 14. And I can subtract 3x from both sides. And that'll leave 2x equals 14. Divide both sides by 2, and x equals 7. So it's asking how long AD is. So then you have to answer the question. Remember, in geometry, you don't always get the answer that's being asked in the value of a variable. We want to know how long AD is, and AD is 5x. So AD equals 5 times our x, which was 7. So therefore, the length of AX is 35. And 7 times 3 is 21, plus 14 is also 35 to check. Okay, so there's example 1. So now you should be able to do problems. So now you should be able to do problem numbers 3 and 4 from the problem set. Okay, example 2, solving a real life problem. Is there enough information in this diagram? So what I've done is I've taken this diagram and just brought the triangle itself out, labeling it K, L, M, and N, just like in the diagram. This is marked congruent to this, so KL is congruent to LM. Is there enough information in this diagram to conclude that point N right here lies on the perpendicular bisector of KM? So when I look at this, I do have a perpendicular, or I have a congruent mark. So I do know that point L is the midpoint of KM. That I do know. But I am not told this is perpendicular. It says, is there enough information in the diagram to conclude that point N lies on the perpendicular bisector? And here's how I'm going to explain this. You cannot always tell if something's 90 degrees or not. So let's just slightly move this to say, oh, I don't know, like right there. I can't even do it. It's because the computer snaps to 90 degrees. But if let me do it this way. Let me get my ruler. And let me put a line segment through L. That's real. Oh, that's going to do the same thing, actually. So let me see if I can do it this way. I don't think it's going to work with this because this is snapping to 90 as well. I can't even get that closer than 3 degrees. Let's make it 3 degrees off. Okay, sometimes 3 degrees is not visible by the naked eye to be. So let's just say we thought this was perpendicular and that N was over here on here. If we don't know that by a 90-degree angle marker that that's 90 degrees, we can't assume it is. So this could be, this angle right here could be 91 or it could be 89. So if it's not perpendicular, then N would not be on the perpendicular bisector. Hopefully that makes sense. So we were told that L is the midpoint and therefore KL is congruent to ML. So this point bisects KM, but we don't have enough information to show that LN is perpendicular. So there is not enough information in this diagram. We are lacking the 90-degree angle. Okay, so now you should be able to do problem number 7 and 8 from the problem set. Okay, a couple more theorems here. Theorem 6.3 is the angle bisector theorem. So it says if a point lies on a bisector of an angle, so here's an angle, angle BAC. If a point lies on the bisector in this case is ray AD. So if point D lies on ray AD, then it is equidistant from the two sides of the angle. So if ray AD bisects angle BAC, so here's ray AD, bisecting angle BAC. If that happens and DB is perpendicular to AB, so if DB, if the distance from that point on the ray is perpendicular, if that distance to B is 90 degrees, and segment DC is perpendicular to ray AC, again, another 90-degree angle at point C, then DB equals DC. Okay, so that's angle bisector theorem. So if we know a ray bisects an angle and the distance from the point on the bisector to perpendicular to the ray is perpendicular to the ray, then those two distances are equal. Theorem 6.4 is the converse of that. So it says if a point is in the interior of an angle and is equidistant from the two sides, so what that means is put D here, but there's no lines or anything here. If you just put a point on, I could have put it here. And then if I drew a line perpendicular to the ray and draw a line perpendicular to the ray, then those two segments are perpendicular. And that you can do that anywhere as long as the point is on the interior of the angle. Okay, so if DB and is perpendicular, segment DB is perpendicular to ray AB, and segment DC is perpendicular to ray AC, and the length of DB equals the length of DC, then ray AD bisects angle BAC. So then we can conclude that angle A or BAD is congruent to angle CAD because angle bisectors cut it into two congruent pieces. Okay, so let's take a look at this example. Okay, here's example 3. It says find each measure. We want to know what the measure of angle GFJ is. The measure of angle GFJ is right here. Okay, so we have a point J. So point J is in the interior of angle GFJ. So 1, we have a point on the interior, I'm not GFJ, GFH. Okay, GFH. So point J is in the interior of GFH. Notice this 7 right here and this 7 right here. That means JG is equal to HJ or JH. Okay, so since J is in the interior and the distance, the perpendicular distance to the ray, the perpendicular distance to ray FH are equal, then we can conclude ray FJ is an angle bisector. Okay, so we now know that that cut this whole angle into two congruent pieces. So if this is 42, this is also 42 degrees. So the measure of angle GFJ equals 42 degrees. Okay, next one. Now we want to find the measure of angle R, or the length of segment RS. So I want to know what the length of this is. Okay, let me use a highlighter for this. Highlighter, make it purple, make it fairly thin. We are trying to find the length of that. Right there. Okay, so that's what we're trying to find. And what are we given? Well, look at here. And we have a point S that's in the interior of angle PQR. Okay, so point S is in the interior of angle PQR. Okay, S is right there. It's in the angle. We have ray QS. How about I do it the right way? Ray QS bisects angle PQR. Okay, since that's true, angle PQS is congruent to angle SQR, and it's marked. All right, the next thing we know is PS is perpendicular to ray QS. Segment PS is perpendicular to ray QS, comma, ray RS is perpendicular to ray QS. All right, so since they're perpendicular and these angles are congruent, so we know this is a bisector, then this distance has to equal that distance. That's what the theorem states. So now we can say PS is equal to RS and substitute our givens. PS is 5x, RS is 6x minus 5, and I'm going to subtract 5x from both sides. And that's going to be 0 equals x minus 5. Add 5 to both sides, and I get 5 equals x. I'm looking for segment RS. So now I can say segment RS equals RS is right here, 6x minus 5. Substitute in our given. We found x, so 6 times 5 minus 5. So RS equals 30 minus 5. So RS equals 25. And if I plug 5 in over here, 5 times 5 is also 25. That's how we check. So the x value of 5 makes this true. And that's how you do this. So now you should be able to do problems numbers 11 and 12. Okay, example 4, solving a real life problem. It says a soccer goalie's position relative to the ball and goalpost forms congruent angles. The soccer goalie's position forms congruent angles as shown. Okay, relative to the ball and the goalposts. Yes. Okay, so goalpost here. Let me use blue, see if that works. So we have the point L. We have the point R, which are the base of both goalposts. We have the point B, where the ball is at that point. And then we have the goalie, who is on this center ray, if you will. And these two angles are marked congruent. So the angle between the ray that if the ball was shot straight at the goalie or shot and hit the left goalpost, that angle is equal to the angle formed by if the ball was kicked to the goalie or if the ball was kicked to this goalpost on the right. So those two angles are congruent. So in other words, the goalie is on a point in the interior of angle LBR, okay, and he's on the ray B, and he's the goalie, so let's call him G, the BGs. Okay, so he's on ray BG. Okay, so will the goalie have to move farther to block a shot towards the right goalpost R or the left goalpost L? That is the question. Okay. So in other words, if this guy kicks the ball on it just inside the left and the ball ends up here and it's a goal, or if he shoots it to the right and the ball comes in and just goes to the left of this point here are the goalposts and there's a goal there, the question is, does the goalie have to move further either direction to stop that ball? Okay, so what do we have? We have a point in the interior of an angle. We have a ray that bisects the angle. That's what these arcs tell us. And so the distance from here over to here is 90 degrees. The distance over to L from the goalie is 90 degrees. And since that's 90 degrees, then they're congruent because BG, ray BG is a bisector of angle LBR. So you can say that. You could say ray BG bisects angle LBR. Okay. Segment GL is perpendicular to line B, segment BL, the ball to the goalpost. Segment G, oops, not GL. Let's call that A and call this point C. I don't know, doesn't matter. Actually, let's call it L sub 1 and R sub 1. So the segment GR L sub 1 is perpendicular to BL, comma, and the segment GR sub 1 is perpendicular to BR. So that means GL sub 1, segment GL sub 1 is congruent to segment GR sub 1 by the angle bisector theorem. So GL sub 1 is congruent to GR sub 1. In other words, moving to the left is the same distance as moving to the right. So will the goalie have to move farther to block the shot towards the right goalpost or the left? The answer is neither. He's the same distance either way. So if the goalie's centered like that, diving to the right or diving to the left would be the same distance to stop the ball. Okay, so now you should be able to do problem numbers 15 and 16 in your problem set. Okay, so here's example 5. Write an equation for a bisector. So it says write an equation of the perpendicular bisector of the segment with endpoints P, -2, 3. So I'm going to plot the point. Step 1, plot the point. Here's P. That is -2, 3. And the point Q, which is over 4 up 1, which is here. So this is Q. And that is the point 4, 1. Okay, so now I'm going to draw a segment from P over to Q. So there's our segment PQ. So it says write an equation for the perpendicular bisector of the segment. So what I want to do, if this is a review question, really, I want to find the slope of PQ. So I'm going to find, actually, we want to find the midpoint. We want to find a point on the perpendicular bisector. So the midpoint is going to be, equal, actually, we just use parentheses here. The midpoint would be x sub 1 plus x sub 2 divided by 2, comma, y sub 1 plus y sub 2 divided by 2. So write a formula, substitute the givens. X1 is -2 plus x sub 2 is 4 over 2, comma, y sub 1 is 3 plus 1 divided by 2. So therefore, the midpoint is going to be the point 4 minus 2, or -2 plus 4 is 2 over 2. 3 plus 1 is 4 over 2. And then simplify the fraction. That's 1, 2. So if I go over 1, up 1, 2, I am right there. And that is the point 1, 2. So now I want to, so I found the midpoint. Therefore, this piece is congruent to that. So I want a line going through this point that's perpendicular to PQ because it's bisecting it if it goes through the midpoint. All right. So that's step 2. Step 1 was graph the points. Step 2 was find the midpoint of that segment. And step 3 is going to be to find the line that goes through that. So I'm going to draw it first, but I need 2 points. So I'm going to wait on that. I need 2 points to draw a line. So I need to find the slope. So M equals, don't mix up the capital M I used here for M. I want the slope of segment PQ, which is lowercase m. So the slope of PQ is going to equal y2 minus y1 divided by x2 minus x1. So the slope of PQ is going to equal first I want to find the slope of PQ. So what's the slope? Y2, 1 minus 3 divided by 4 minus a -2, which is 4 plus 2. So the slope of segment PQ equals -2 over 6, which equals -1/3. So this is the slope of PQ. Down 1 over 1, 2, 3. Down 1 over 1, 2, 3. Okay. Well, if you don't remember, the slope of a perpendicular is the negative reciprocal. So now I'm going to use the equation y equals mx plus b. And I can choose, I use this point right here. This is my x, this is my y on this line. So I'm going to put y is 2 equals the slope of a perpendicular is the negative reciprocal. So flip this over, it's 3 over 1 and it's positive. So my slope is 3, my x is 1, and all I have to find is b. So 2 equals 4 plus b, subtract 4 from both sides, and I get b equals -2. So that's my y-intercept. So here is b right here. Now I can draw my perpendicular bisector. So I'm going to draw it as a ray. So let's have arrows at both ends, make it a little narrower. And I'm going to draw it like so. And of course, if I were using a ruler, I wouldn't have to do this. So obviously you can't do this on paper. Okay, so there's our perpendicular bisector. Okay, this is 90 degrees. This segment equals this segment. And the equation of the perpendicular bisector, now we want to put everything together now, is y equals our slope, 3x, plus b is minus 2. So the equation of our perpendicular bisector is y equals 3x minus 2. Okay, so with that example, you should be able to do problem numbers 19 and 20 on your problem set. Okay, this page brings us to the end of chapter 6.1. Please do these exercise problems. 39 through 44 are review questions. Okay, thanks for watching and have a great day.